on game theoretic models in all kinds of areas of pragmatics. So he worked on Gricean pragmatics. He worked also on social meaning and on historical linguistics and language change. And I'm very happy that he is now one of my colleagues. And yeah, I think I give the word to Roland.
Okay, thank you very much. So how does it work that people can see my screen?
Yes, share screen.
Ah, okay.
And then pick up the...
I have to do this iPhone. Okay, excellent. Okay. Okay. So I hope everybody can hear me and see my screen. So, okay, let's start. So today I want to talk about bargaining games or a specific type of bargaining games. But before I start, I just want to introduce the people I'm working with on this paper. We're working, this is a collaboration with Jeremy and Michaela. And we also had a lot of interesting insightful sessions where Christoph and Anton were involved. So we're kind of a team at ZAS, and we call ourselves unofficially the social meaning and game theory team. And this is what I will talk about today. So I will start more with a model-based view at the beginning, and then later related to real-world phenomena, but not in very much detail. So the basic problem that I want to discuss today is the division of joint resources. So this is often a problem in society. The fruit of our joint labor is this distributed in a fair way. And this is, of course, not easy to define what a fair distribution is. However, we start with a minimalistic example where we think about two parties or two agents who have to split a specific resource. And the idea is that they're interchangeable in a way that a fair split would be if both get the same amount. So here's an example. We have a pizza with 10 slices. So this is the amount of the resource here is size 10. And then both parties can make a bid that is between 0 and the maximal size, in this case 10. And then if the amount of both bids is below this value, then both parties get what they want. So if I bid for 4 pieces, if I want to have 4 pieces, you want to have 5, we get our pieces. 1 piece is left, and this gets, for example, our dog. Yeah. So this is waste for us. And now, if both bids are above this value, then bargaining fails, and then the whole resource is wasted. So while we are fighting about it, our dog is eating the whole pizza, for example. And then we can have a backup value. So we can have a sandwich in the fridge, and I have a bigger sandwich than you, then I have a bigger backup value, and what this backup payoff, and this is called the disagreement point. In this example, we would have 11 strategies, right, from 0 to 10. And I would like to even simplify this scenario to a more general one where we have only 3 different kind of choices. Let's stick with the example that a maximal resource size is 10. And then we say that we have a medium bid that is 5. And then we have a low and a high bid. The low bid is below 5 and the high bid is above 5. So above or below the half of it. And let's make it even more concrete. Let's say the low bid is 4 and the high bid is 6. And then when we have this in Brüggens, we can have a normal form game of the situation. This is a game theory description of the situation where we have 2 players, player I, player J. They have these 3 strategies. They can bid between L, M, and H. And then we can, for each combination, we got 9, so to speak, strategy profiles. These are combinations of strategies. We can then look how the utility for specific players look like. For example, if I look for the player's E utility, I see when as player I bid L, I always get 4. If I bid M, I get 5, unless the other player bids H, because then we're above this 10 size of 10, and then I got my disagreement point. And so we can add the utility values of the other player to it, and then we got this utility table for each combination. The first value again for player I, the second value for player J. This is a so-called Nash demand game. And this, in this definition, this game is asymmetric simply for the reason that the di and dj doesn't have to be the same. And we are looking especially in this kind of cases. Furthermore, we assume that di and dj is below 4, whereas we will later consider 4 as an extreme point. But when we have this definition, we have 3 so-called strict Nash equilibria. These are strategy profiles where no player has an interest to move away. Each player would lose something. And these 3 strategy profiles are exactly these boxed strategy profiles you see here. And let's, for example, see the strategy profile H and L. So as you can see, player I has no interest to move away, because here she gets 6 points or 6 slices, and if she would move away, she gets strictly less. And player J gets 4 here, and we know that DJ is below 4, so also player J would get less. And you can make the same calculation for the other strategy profiles. Now, this is a 2-player situation, and now we try to put this in a population-based setting, or we take a look from a population-based view on the scenario. And we also distinguish between 2 types of groups that we will call the blues and the reds. And these groups differ in a specific property, and this is either DI, so the disagreement point. So we make a simplification that all blues and all reds have the same disagreement point, but they might have different disagreement points. Yeah, so different backup values where they can fall down to when bargaining does not work. In the other scenario, we assume that the disagreement points are the same, but the population size is different. So both groups have a different population size, and this is here defined by PI and PJ. And we assume throughout these examples that the blues are the dominant group, so they might have a greater disagreement point, or they might have a greater population size. Furthermore, we assume intra and intergroup interaction. That means that the blues play this Nash bargaining game pairwisely with themselves and with the reds, and the reds likewise. But we have only intra-group replication or imitation. So the strategies the blues use, you have to assume now that we have kind of a repeated game, or people interact over and over time, and then they adapt their behavior according to dynamics of evolution or learning. We will come to these details later. Now, in this scenario, agents can learn conditional strategies. This is a very important point. So, for example, a blue could learn that he makes always a medium bid when he meets another blue fellow, but he makes, for example, an H bid when he meets a red agent. And this would be a conditional strategy where I behave differently with respect to whom I meet. Let's formalize this. So a simple conditional strategy has 2 aspects: the bid I make with members of my group, BM, and the bid I make with members of the other group. And if we analyze this kind of game, and study the different kind of conditional strategies that might evolve under evolutionary dynamics or learning dynamics, and which are so-called evolutionary stable, a concept that is strongly connected to a strict Nash equilibrium, then we find that there are 3 of these strategies. One is a fair strategy, that the blues and the reds play, make the medium bid with everybody, so everybody splits fairly the pizza. With a pro-blue strategy, where the blues make the medium bid, the 50% with themselves, but the high bid with the reds, and the reds make the medium bid with themselves and the low bid when they meet blues. So this is a pro-blue profile, because the blues exploit, so to speak, the reds, because they get just more out of the interaction with the reds. And the pro-red conditional strategy pair is exactly the opposite. Now, if we study this game with a very simple two-population replicator dynamics, this is an evolutionary dynamics that simply says that the populations play this game, and the more successful a specific strategy is, the more probable it will be replicated in the next round. And for example, and what you see in this diagram here is we test the different disagreement points of the blues. The disagreement point of the reds is 0. We assume this 0. And let's say when the one of the blues is also 0, what we find is when we start with a random sample of different kind of population states at the beginning, this is similar to every agent starts with a random strategy, then this process ends up in one of these three evolutionary stable states, what we will also call norm. And we can, when we make, for example, 1,000 runs, compute the probability or the frequency a specific strategy emerges. And in this case, the fair norm emerges with more than 60%, and the other norms around 10%. And then there are also other outcomes that I did not reconsider here, but these are the three most important ones. But what's more important is if we make the same experiments but increase the blues disagreement point, what we see is bit by bit the emergence of the fair norm decreases and the emergence of the pro-blue norm increases with the disagreement point of the blues. And we can make the same experiment, but this time the disagreement points are the same, but the population size of the blues increases per experiment, and we see a similar effect that when the more the blues are in majority, the more probable this pro-blue norm emerges. And we call this two effect, we call the bargaining power effect on the left. On the right, we call this the red king effect. So let's just summarize at this point. These were results that were already, discovered by others. So there's a red king effect that demonstrates how minorities could come to be systematically disadvantaged in virtue of their minority status alone. So we need nothing like a policy or something who takes care for this, just interaction of utility maximizing agents would produce this effect. The bargaining power effect shows that if a group with a higher bargaining power can successfully exploit this and get a bigger part of the resource. And this points also what Nash called a threat point, but you have to reconsider this. Consider that this model does not take any assumption about agency. So these are really processes that just happen out of the interaction, out of repeat interaction. But one important feature in this kind of model is that we need to observe the features of group affiliation. So this kind of model really nicely explain when we have groups where we can clearly see when we meet somebody, we can clearly allocate this person. And typical examples are gender, skin color, ethnicity, obesity, as we just had, you can directly see, or maybe body height could also be an example. But we are also interested in features that are not directly observable: social class, wealth, political affiliation, religion, you name it. And because when you meet somebody, you don't know how rich the person is. Of course, the person can signal it, but then this is something else. But alone, the money you have on your account, I cannot see when I meet you. Now, we would like to extend the model we saw so far with the idea that these features, to be blue or red, is directly connected to being a majority or being having a higher disagreement point, is not directly observable, but it can be signaled by what's a model extension, what is called pre-place signaling. And we will now take a look at 3 different models. And the first model is integrates the idea of strategic signaling. So the idea is that a strategy, as you saw it before, has a third component. This is the signal an agent can send. And then the conditional strategy looks like this triple here, and it says, it defines the signal an agent can send, then the bit an agent makes to another agent who uses the same signal, and the bit an agent makes with another agent who signals a different signal. We test the minimal version here, that the space of signals has only 2 signals. I call them here S and S prime. And then if you test this under an imitation dynamics, but it doesn't matter, other dynamics will reproduce similar results, as we found out. And I don't want to go into details how this dynamics work. This we can discuss later. But important is that there are 4 relevant strategies that emerge. The 3 we already saw. So the fair one, the pro-blue and the pro-red. A precondition of pro-blue and pro-red is, as we will also see in the results, that agents send different signals and recognize each other. And there's also a strategy that can happen if the disagreement point of the blues is very high. It's called unconditional pro-blue, where the blues always a bit high and the reds always a bit low. But this only happens if agents cannot distinguish each other. So when they send the same signal, so to speak. Okay, let's go to some experiments. The first one in this setting is we call matching group experiment that pays respect to the initial setting. So what you see here is that the blues start with a strategy set, and you see the symbol of the dice, and the dice means a random strategy. So how agents behave initially is defined randomly. What is fixed at the beginning is that all blues start with a different signal than all reds. And what we see is the same effect in this aspect when we test for different blues disagreement points. This is exactly the bargaining power effect we saw under replicator dynamics. This is completely expected. It's clear because the signals directly signal, so to speak, the group affiliation, yeah, from the beginning. And when you make, then we made a second experiment where the initial signals are also randomly chosen, S or S prime. And what we see is that the fair norm is emerging much more often, and only for very high disagreement points, the unconditional pro-blue strategy gets more successful. But the pro-blue strategy that was successful in the first setting is not successful at all. And the reason is simple to explain. If we also recorded then for all simulation runs the average time that distinctive signaling emerges. Distinctive signaling means one group uses one signal, the other group uses the other signal. Of course, in the first experiment, it's always 100% because this is a starting condition. In the other experiment, this distinctive signaling emergence is unbelievably low. I mean, it's very low. So in a neutral setting, you would expect this to appear 50%. Because there are 50% outcomes where distinctive signaling could emerge in, a 50 that they could not emerge in, without going into details. But this value is much lower here. So the surprise is not that pro-blue cannot emerge, because pro-blue needs distinctive signaling to emerge. The bigger surprise is, why is distinctive signaling so low here? And the reason we can find, or an explanation we can find, if you look for a third experiment where we, for example, start only the blues have an established signal at the beginning, and the reds have a random signal. And what you can see is, in this kind of experiment, also fairness emerges very often. And you see that the reds so distinctive signaling is very low, so they very often adopt the signal of the blues, because this is around 10%. So in around 90% of all simulation runs, the reds adopt the signal of the blues, say so-called camouflage. And this prevents the pro-blue norm to emerge, and this helps the fair norm to emerge. If you make this opposite experiment and the red starts with a fixed signal, then you see that the pro-blue norm emerges. You see something like a weakened bargaining power effect, and you see that distinctive signaling increases with the blues disagreement point. So here the blues try to develop a signal that is different. So they try to increase the chance for distinctive signaling to establish the pro-blue norm. Putting this together is, since the camouflage of the reds is unconditional, this seems to have a stronger effect of the overall results if both groups start with a random signal. So to put this results of experiment 1 to summarize here, the first point is obvious. Conditional strategies such as the pro-blue strategy needs a distinct signal to evolve. But these red agents have the unconditional tendency to camouflage. And so they make fairness much more probable to emerge. Whereas blues agents have a but conditional tendency to mark themselves off. And this together shows that starting with random signals makes ZAS and therefore the emergence of fairness very unlikely and enhances the probability of fairness to emerge. So it strongly mitigates the bargaining power effect. And I don't show you the results here, but we made the same test with different population sizes. Like the blues are more and more majority, and it has a similar impact on the so-called red king effect there. Let me go to the second model now. In the second model, we let agents probabilistically send signals. So agents can, for example, we reconsider 2 signals again. An agent can, for example, with 80% signal S and with 20% signal S prime. We use the same dynamics. We only reconsider the most prominent resulting strategies that we find. This is again fair and pro-blue. And but this time we did the experiment in a way that for each experimental setting, we set the probability distribution for both groups fixed. So this value is fixed, but can be different across for reds and for blues at the beginning. So what is changing over time is only the strategic behavior. And we tested different kind of combinations of the probability that agents signal S and the red signal, the blue signal S and the red signal S. And if you look, so we use value 0, 0.25 and so on until 1. And if you make for all combinations, again, a number of simulation runs, let's say 100 here, I think there were 100, you can compute how often the fair equilibrium emerges. This is kind of a heat map here. You see the higher the value, the hotter the color. And you can see that also not surprising, first of all, the corners here, bottom left and top right are the ones where agents use completely distinctive signaling, and there the fair norm does not emerge very often. Let me put the heat map for the pro-blue norm. This looks like a mirror image. The pro-blue norm emerges here very often. When there is noise, you see the fair norm emerges much more often, but what you can also see is that there's a specific asymmetry. When you move away from an extreme point, let's say here, you can see if the blues, for example, would change their signal a little bit in the direction of the reds, they could do much more they could much more easily establish the fair norm to emerge, whereas the reds have to change much more their signaling behavior to reach the same effect. And this is a dilemma in itself, because the group who has interest in the fair norm has much harder times to reach it, has much more change to the other signal, whereas the group who could easily change it has no interest, because blues profit from the blue norm. So what we see here is that, as you saw, a little bit of noise is often enough to establish fairness, that the groups don't recognize that easily each other. But then we saw this asymmetry between blues and reds that form a dilemma in itself. And we also did the same experiment with different population size. So we paid respect to the red king effect here too, and we got a very similar picture here. And now I come to the third model that here we take a look at a continuous signaling space. And let's say we have a multidimensional space, and the signals are this time not just entities of a discrete set, but they are coordinates in the signaling space. And you can compute the Euclidean distance between, for example, or an agent can see the distance between his own signal and the signal of another one. So I can see how far away your signal is from mine. And agents have a tolerance radius, and then we say, if you are inside my tolerance radius, then you're in group, otherwise you're an out group member. And then we can again define this kind of a strategy where we send a signal that's somewhere in the signal space, and then we can define how what kind of bit we make when we meet in-group agents and what kind of bit we make when we meet out-group agents. And we have another factor in it. This is called what I call alignment strength, and this defines how strongly I will show you on the next slide how it works. It's easier to show in the figure. So here's the experimental setting. We have a population of 50 blue and 50 red agents. This is just a dummy image to show you how it might look like. There's only 10 and 10 agents here. And then all agents have initial strategies. They also have initial signaling positions, but we put them in a way that the blues are in one part of the space and the reds in another part of the space. By the way, as you can see, this is a two-dimensional space here. And then the different tolerance radii are also taken from a normal distribution, that they are not too different, but they are different, a little bit different at least. And then we made 5 experiments with respect to different alignment strength values. Just give you an example of alignment strengths. Remember, we are looking at the imitation dynamics. When this agent down here, you see this red arrow here, hopefully, wants to imitate this agent here, then if the alignment strength is 50%, he's not taking his signal completely, but he is moving 50% in the direction of the other agent. And if the alignment strength is only 20%, for example, moves only 20% in this direction. So we made 100 runs per session, and here are the results. First of all, we find out that in a number of simulation runs, a so-called segregated society emerges, where there's almost no overlap between blues and reds. And in other runs, an integrated society emerges, where blues and reds have a large overlap. And we can measure this. One way to measure this is called what we call neighborhood diversity. And this is just, we average over all agents. And for each agent, we compute the value of how many other agents are in my neighborhood. My neighborhood is the agents inside my tolerance radius. So how many of the other color are in my neighborhood divided by how many of my color are in my neighborhood. And if this value is below 1/2, like in this example, it's probably 0 here even. This is an extreme example. We call it a segregated society, otherwise an integrated society. And the probability that this emerge in this setting is, we find 63%. This society emerges in 37. The integrated society emerges. But these numbers, of course, change if you change the threshold here. The more important point is that we have a reasonable number of runs where one or the other outcome emerges, because we like to see what kind of norm emerges independence of this outcome. And this is what we did. So we look at, remember we made experiments with different alignment strength, and we looked at how often the pro-blue norm emerged for runs where a segregated society emerged and where integrated society emerged. And not surprisingly, in a segregated society where agents are far away from each other, blues are on one corner, reds on the other corner, there's a clear distinction of blue-red with respect to in-group, out-group. We find the pro-blue norm to emerge, right? But if we have an integrated society, it does not happen. So completely expected result. And if you go further, you see that the emergence of problem roughly goes a little bit down, but it stays, it's not significant, it stays until the end around 80%. What's more interesting is that when we have very low alignment values, the pro-blue norm emerges even in integrated societies. And that's surprising because integrated societies don't really differentiate between blue and red anymore. They have all kind of mixes in their neighborhood. And how is this possible? And the reason is that, remember at the beginning of the experiment, both groups were segregated. And what happens is because they adapt the signal so slowly, they first learn the oppressive norm and they afterwards move together to integrate. So, and this integration process also leads to large neighborhoods where I have most of the other agents in my neighborhood. And so I see many fair bits or fair splits, or a lot of fair behavior. Why? Because remember, pro-blue and pro-red say play fair with in-group members, but play unfair with out-group members. And if I have most of the people in-group members, I see most of the time fair behavior. But this fairness is superficial because agents have early on learned the oppressive, or from a red point of view, a conceding norm. And this is intrinsic. They still have the norm. So what this means is every outsider who comes new to the society in some way here will be treated unfairly. Okay, now I think my time is almost up, or it's up, so I come to the summary. What I at the beginning showed you is that unfairness in this Nash demand games needs only minimal conditions to emerge under dynamics of social learning and cultural adaptation. What we only need is utility maximizing agents. We need clear group recognition, so I have to clearly see who belongs to my group, who belongs to the other group. And then when we have a global asymmetry across groups, either in bargaining power or in group size, we get this kind of effects that produce oppressive norms. Then we took a look at what happens if this is not clearly observable, if I'm blue or red, and what happens if we have pre-placed signaling possibilities. And we can see that distinctive signaling is necessary for the oppressive norms to emerge. And the reds unconditionally camouflage and therefore strongly work against this emergence and make fair norms more probable. In the probabilistic model, we also saw that a little bit of noise, so it's kind of a similar effect, is enough to produce fairness. And we saw this interesting asymmetry between how strongly somebody has to deviate from a pure signal to make fairness more probable. And then in the last model, we saw that oppressive norms generally co-evolve with segregated societies, but we saw when the signal adoption is slow, oppressive norms can co-evolve with the integrated societies, and we see superficial fairness, where agents treat each other fairly, so make always a fair split, but they have learned the unfair intrinsic norm, and every new outsider would be treated unfairly. Thank you.
Yeah, thank you, Roland. The floor is open for questions.